When we look at nuclear reactions, there seems to be two major patterns or major types of nuclear reactions. The first one is called radioactive decay. In radioactive decay, what we're doing is taking an unstable isotope and making it stable. So we take an unstable isotope or an unstable nuclei. It releases particles or photons or both to become stable. Now remember, photons, back in Gen Chem 1 when we talked about photons, that was light energy. So an unstable nucleus becomes stable either by releasing a particle or particles and releasing energy or releasing energy. It's going to be one or the other or both. Okay, so that's the first type of nuclear reaction that we come across in nuclear chemistry. The other type of reaction is called nuclear transmutation. Nuclear transmutation, where we bombard a nucleus with particles to convert that isotope into something else. There are 5 basic particles that we use. We talked about 3 of them in the last video. So we're going to introduce the others that to you. So the first one is the proton. Okay. And so the way that we write a proton, we're going to write this using the nucleide symbol. By the way, if you remember the nucleide symbols, and this was one of those things probably introduced at the very beginning of Gen Chem 1, you start with the atomic symbol. So if we were writing the nucleide for helium, we would write the symbol for helium. In the upper right hand corner, you're going to put the mass. So the mass of a helium atom is going to be 4. In the lower left hand corner, you're going to write the atomic number. Okay. So again, in the lower left hand corner, this is going to be your atomic number. In the upper left-hand corner, you're going to have the atomic mass. Okay, so when we're writing the proton would be written with a lowercase p. It will have a mass of 1 and an atomic number of 1. Now, the other way of writing that, if the species that has a mass of 1 and an atomic number of 1 is the hydrogen atom. So you could write a proton using a lowercase p, or you could write a proton using the hydrogen. Okay. The other type, the other particle inside the nucleus is the neutron. Okay. And we write that with a lowercase n, and the neutron has a mass of 1, but has no atomic number. Okay. And there's only one way to write a neutron, so we're good. The other basic subatomic particle for the atom is the electron. And to write the electron, there's 2 ways to write this. We could use a lowercase e, where the electron has no mass and has a -1 charge. It has an atomic number of -1. The other way of writing this, you have the 0 for the mass, -1 for the atomic number, but instead of writing lowercase e, we use the Greek symbol beta, because the electron we refer to the electron in nuclear chemistry as a beta particle. Okay. Now, there is something that's the complete opposite of the electron. So let's say you had an electron that has a mass of 0, but instead of having a -1 charge, it has a positive 1 charge. So it's not the proton, because the proton has mass, but the opposite of the electron is called the positron. Okay, so the positron has a mass of 0, but it has a +1 charge. Okay, so you could write it as E with a mass of 0, nuclear atomic number as a +1, or you could write the same thing, use the beta particle. Either way. Okay, so again, let me make a note here. The electron, we refer to that as a beta particle. All right. So positrons are the same, have the same mass as an electron, but it bears a positive charge. It's like the antiparticle of an electron. The other major type of nuclear particle that we come across is going to be called the alpha particle. Okay, the alpha particle, we write this with the Greek symbol alpha, and it's going to have a mass of 4 and an atomic number 2, which is, by the way, the same thing as saying helium. So sometimes we write instead of writing the alpha part, writing the Greek symbol alpha, we could write the atomic symbol He for helium. It means the same thing. It's the helium atom stripped of its 2 electrons. Now, there is one more particle that we talk about. And when we're balancing nuclear equations, these are the main 5 that we use. There is a 5th one, though. There is a 6th one, and that is called the gamma particle. Gamma particles are just pure energy. So for a gamma particle, we write the Greek symbol gamma, but it has no mass and it has no atomic number. It's literally energy. Okay. All right. Now, for balancing a nuclear equation, there are 2 basic rules that we have to follow. The first rule is this. The atomic mass on the product side has to be the same on both sides of the equation. So whatever is on the right-hand side, the left-hand side has to add up to that number as well. For the second rule, same thing. We're going to take the atomic number. Whatever the atomic number is on the left, it's got to equal on the right. And so that's pretty much how we balance a nuclear equation. And we talked about how do we write nucleides. We write the symbol for a species that has 18 protons, 18 neutrons, and 18 electrons. So the atomic number with 18 is going to be argon. So 18 goes in a lower left-hand corner. If we add 18 plus 18 together, that gives you 36. So that's your atomic mass. That's going to go up in the upper left-hand corner. What if you have something like 28 protons, 31 neutrons, and 26 electrons? That 28 protons would be nickel. So we would write the symbol as nickel. 28 as the atomic number, and then 28 plus 31 will give you 59. So this is going to be nickel 59. But to show that it has too few electrons, we're going to write in the upper right-hand corner the charge, +2. All right. Now, remember, we talked about isotopes before. Remember that isotopes have the same number of protons but different number of neutrons. So would two isotopes of the same element differ a lot, not a lot, or would not differ? They would not differ in the properties. The only difference is the number of neutrons. So that's it. All right, so now that brings us to our problem. We need to balance the following reactions. So let's take a look at problem number 1. Uranium-235 plus neutron yields barium-142 plus krypton-91 plus 3 neutrons. All right, so we need some information before we go. First off, since everything is written out in words and not symbols, we need to write the symbols. When we write the symbols, we need the atomic numbers. Okay. Now, the numbers that come after the name, so like for instance, if we take a look at uranium-235, that number indicates the mass. So if we have uranium, that has the atomic symbol capital U, the 235, that would be your atomic mass. So that means we have to look up its atomic number. On the periodic table, the atomic number for uranium is 92. So that would be the nucleoid symbol for uranium-235. We're going to add a neutron to the mix. Okay, so remember that we write the neutron as a lowercase n. It's going to have a mass of 1, has 0 for the atomic number, and so that's the left-hand side of the equation. Okay, so let's write the other one. So the right-hand side. So you got barium-142. So the atomic symbol for barium is Ba. The mass is going to be 142 because we were told that in the problem. But if we look up barium on the periodic table, the atomic number of barium is 56. Okay. The next one is krypton-91. So the atomic symbol for krypton is Kr. We know the mass is 91. And then looking up the atomic number on the periodic table, krypton is at 36. Okay, and then we have to add in 3 neutrons. So the way that we do this, I'm going to write the symbol for neutron again. Okay, so neutron has a mass of 1, has 0 for the atomic number. Now to indicate we have 3 of these, I'm going to put a 3 in front of the neutron. Okay, so there we go. Now, so the only thing is we've got to make sure that these numbers balance out. Okay, so on the left-hand side, let's add up the masses. So you've got 235 plus 1. So the mass on the left-hand side needs to be 236. For the atomic number on the left-hand side, you got 92 plus 0. So that's what we have for the total atomic number on the left-hand side. So what that means is that on the right-hand side, everything's got to be balanced to that. So if we do let's do the atomic number on the right-hand side, you got 56 plus 36. So that's going to give you, that's going to be 92 for your mass. So for your number, so we're good on that. So 142, okay, plus 91, that should get you, that should give you 233, plus the 3 neutrons should get you 236. So yay, we're good. So to balance, this is your final balanced nuclear equation based on what this reaction is describing. Let's try another one. This is more our style as to what's going to be in your homework. So here's your bismuth 189. So the symbol for bismuth is Bi. We know the mass is 189. According to periodic table, the atomic number is 83. Okay, so that's your left-hand side. So that's great. You know exactly what your numbers are going to be on your left-hand side. On the right-hand side, you're told alpha particle plus something. We don't know what that question mark is. So we actually have to figure this out. So the first thing we have to do, let's write the symbol or the symbol for the alpha particle. So that was has a mass of 4, atomic number 2, and that's your alpha particle. Now to figure out the thing that's missing, we're going to take 189 for the mass on the left-hand side and subtract 4, and so that's going to give you the mass, the missing nuclide. Okay, so 189 minus 4 gives us 185. For the atomic number, we're going to take 83 minus 2, so the atomic number should be 81. Now, according to the periodic table, the species that has the atomic number 81 is Tl. And there it is. So this would be your missing species. And that's how we write a balanced nuclear equation.